Okay, that again is February 24, 2022, and we are talking about motion of an electric charge in a uniform electric field. So again, remember, two parallel plates is like this one that has sizes that's very large compared to the separation is going to generate a uniform electric field. And this configuration is very sturdy. Works pretty well. In reality, you don't need to have a small separation. You saw in the experiment that the large separations also work pretty well for uniform electric field. Okay. So what we're going to do? We are going to find out what happens with an electric charge when it's in between, whenever it's subjected to a uniform electric field. Okay. So if you put an electric charge, a positive electric charge at rest close to a positive plate, to the positive plate, what's going to happen? You have a charge of mass m, charge q. Okay, don't forget outside the electric field is going to be 0, inside the electric field is going to be different of 0. And we found out what is going to be this electric field from the derivation I gave to you, right? So here, let's just remember what is the electric field. Here we go. Is the electric field is something like that. Twice kq over r square for one single plate. If you have two plates, okay, remember one single plate. If we have one single plate has a uniform electric field given by the field on single plate of charge q and radius r has a uniform electric field given by something like that. This thing can be further simplified, okay, oh, if you write this equation in terms of the area. Okay, don't forget, if we put like a pi right in here, we have to multiply by pi as well. There's a reason why we do that. Okay, well, pi r squared is going to be what? It's going to be the area of the plate. Okay, and q divided by a has a name. Q divided by a is the surface charge density. It's like that. This surface charge density. And that's another format that we get for the electric field of a surface charge distribution. We can here write that in a different way in terms of a constant that we call the dielectric constant. The dielectric constant is what? Is 1 divided by 4 pi epsilon epsilon epsilon. Oh gosh, I heard that. I hate that. Epsilon naught. Let's try it again. Epsilon. Ooh. Oh gosh. Pi epsilon epsilon. Yeah, doesn't get it. Oh yeah, good. Epsilon naught. Where epsilon naught is called the dielectric constant. That's another way of writing the same equation. That's the way that you're usually going to see out there in terms of the epsilon naught, not in terms of the k. Okay, and then we can further simplify. Okay, you get sigma over epsilon naught. Now you choose which one is easier to memorize, if it's this one here or if it's this one right in here. Okay, but remember, that's just for a single plate. A single plate, going back to a single plate here, has an electric field that's equal to sigma over 2 epsilon naught. Okay, whether the charge is positive or negative, the strengths, sigma over epsilon naught. Now when we put two plates next to each other, okay, the field inside doubles and the field outside becomes 0. Okay, for two plates, let's write it down. For two plates next to each other, one positive, and another negative, the field within the volume of the two plates doubles and becomes negligible outside the volume, outside this volume. Okay, so for two plates, the field within the volume is, okay, here we go. Don't forget that those are all approximations, but even more important, those are very good approximations. It's not just any type of approximation, but it's a very good approximation. So it's going to be twice that the field of a single plate, okay, which ends up being sigma over epsilon naught. That's the formula that we usually see out there. For some reason, people books don't like to use K's in the electric field for this type of configuration. Okay. Two plates, for two plates, the field within the volume is, whereas outside the volume, the field is negligible or 0. Okay? It's a uniform field. This is a uniform field. Okay, and now, because it is a uniform field, the force applied to an electric charge within this volume is going to be constant. Okay, the force, because the field is uniform, and what does it mean uniform? Constant in space, right? The force applied to a charge will also be uniform or constant in time. Okay, so we can write it down. Force applied to a charge q. Let's put like that. Charge q. Okay, force times, I'm gonna put just electric field here. Simplify my notation. I don't need to put the direction of the field. Okay, so here go, I will. And also, don't forget, this is gonna be an approximation, right? Well, this one is not approximation. The approximation is gonna be the next one. Okay, the next one will be an approximation. It's going to be Q, okay, times sigma epsilon naught. Don't forget, the sigma here has a Q that's different from this one, okay? Has a Q that's Q of the plate. Q of the plate. Okay? Using Newton's second law, we can find the acceleration of this charge of mass m, or here it goes, assuming that there is no other assuming that there is no other forces, okay? Assuming, here you go, assuming that there is no other force other than the electric force. As I mentioned to you before, don't forget, the electric force rules supreme in the microscopic world. In the microscopic world, the gravitational force is negligible, okay? The gravitational force at the microscopic level is negligible. Okay, net force is going to be, and this thing is going to be, since you are talking about net force here, okay, what goes on the right side is going to be mass times acceleration of the charge. And the acceleration of the charge is going to be go Q over M. Okay, that's going to be like that. Recall this ratio here. Remember this ratio, Q over M. There are experiments that are specifically designed to determine this ratio between the charge and the mass. Okay, just remember that. And don't forget the sigma here. I'm going to write that for you. This sigma here. Again, that should be an approximation, right? Because it's the net force. But again, it's a very good approximation. I'm going to write this little q here as being the charge in the plate. I'm going to distinguish of the charge in the plate as lowercase q divided by the area of the plate. Here's the charge that's subjected to the electric field. Here is the charge that's generating the electric field. Okay? Which is the charge of the plate. And the acceleration is something like that. It's a uniform acceleration because the charge doesn't change, this charge doesn't change, the mass of the particle doesn't change, this charge doesn't change, this area doesn't change, the area of the plate doesn't change, and the epsilon naught is a universal constant. Okay, and then you get something similar for a charge being, projected inside this volume with a velocity perpendicular to the electric field. What you see right in here is exactly the case of is the case similar to that of a projectile motion. Okay, so here you go. Let's get this projectile here. The first case that you saw, this case is something like that. The charge is not that something like that. It is analogous. Is the electrical analogous of the free fall charge. Okay, the free fall particle. Electrical analogous. That's what you see here. This other case here that you see is the electrical analogous of the projectile that's propelled with a given velocity perpendicular to the force and describing a parabolic motion. Okay? See, the velocity is perpendicular to the force. And you can go ahead do the same calculation that we did for projectile motion. That's what we have, okay, for 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 this chapter, and that's the chapter of electric field. Right in here. Nope, this is not the one. That's the lab. Here we go. So we are done with the chapter on electric field. We cannot cover everything that's in there in the book, okay? So, and now we're going to get into chapter 24. That's the Gauss's law. Great. Any questions about that? Okay, so let's see what. Okay, so I showed to you how to calculate the E field of charge distributions using Coulomb's law. Coulomb's law. Coulomb's law. There is another way of calculating the field using a simpler mathematical technique. Technique referred as Gauss's law. Coulomb's law. There's something wrong with this Coulomb here. From electric field. So, and what is Gauss's law? Coulomb. Okay, Coulomb's law. I had written that before, right? But for some reason he didn't like it. Huh. Yeah, now he didn't complain. Gauss's law. Gauss's law, yeah. Let me show you how Gauss's law works, okay? First let's formulate Gauss's law. First, let us formulate Gauss's law. Gauss's law is nothing more, nothing less than the integral format of Coulomb's law. Okay, the integral format of Coulomb's law. Coulomb's law. And how does it look like? Okay, I'm gonna give you the integral format, and that's how we are going to start, and that's how we introduce the laws of electricity and magnetism in this course. We introduce the laws of electricity and magnetism as in the integral format. So the way we do is like that. We put an integral here. Start to get familiar with this integral format, okay? Integral, here we go. we have the electric field. The electric field, don't forget it's a vector, the electric field. I want to stay consistent with my notation. Let's see. Yeah, I use the A as the area. Okay, I use the A as the area, dA. And the A is also a vector. So let's go ahead and put the vector sign there at the top. Over bar. Here we go. This one. And the E is also a vector. So I'm going to put a vector here first and then change to D to, to E. But there is one more thing. Vectors, they don't multiply in this way, okay? What we have here, we have a vector. This guy is a vector, and this other guy here is also a vector, okay? So there must be an operation between those two vectors, and this operation is the scalar product. Can you remember that? E dot dA. E dot dA. This thing here is integrated over yeah, this thing here is integrated over the area. I'm gonna tell you which area is this one. Okay. Oh, by the way, there's more to it. I've used the wrong integral. The actual integral that we use you go, this one here. Okay. This circle that you see in there has an interpretation, has a meaning. Okay. We are integrating over the surface of a given surface. I'm going to tell you exactly what this surface is all about. And this surface must be a closed surface. That's what this circle is all about. It's two integrals because it's a surface in the two-dimensional space, right? Is a is an integral over a surface. A surface is a two-dimensional is a two-dimensional object. And then we have something else too. We have Q on the right side, but it's a special type of Q. We call it enclosed Q. And divided by epsilon naught. Can you remember that? That is one of the laws of physics. Like I said, this already has Coulomb's law implicit there inside. Coulomb law is just a special case of this integral. Let me write that down here for you. Coulomb's law is just a special case of this surface integral. And you're going to see why. Scientists, when they're doing experiments, they came up with this law. And now what is this enclosed, Q enclosed? What this Q is all about? What Q is telling us? Q is telling us that it is the source of the electric field. Okay? In order for you to have an electric field, you have to have an electric charge. In order to have a gravitational field, you have to have a mass. Okay? So it's the same thing as the electric field. The source of an electric field is a charge. It's an electric charge. And it's the charge, but it's the charge that is enclosed by this surface. That's what it's all about. The charge that is enclosed by this surface. That's how you should interpret. Okay. Q enclosed is the charge enclosed by the surface in the integral. This surface in the integral is called the Gaussian surface. Lots of things to remember, right? Gaussian surface is a closed surface. And this term that you see right in here has a special name. This term that you see right in here is called the flux, electric flux. Okay. E dot dA is called the electric flux through an enclosed surface. The electric flux through an enclosed surface. It is represented by, is usually represented by the, by the phi, by the letter phi, capital Phi. And what we're going to do now, we are going to solve some problems in terms of the electric flux. So you can have a feeling exactly of this integral is all about. And then we worry about the enclosed charge later on, okay? I have some illustrations here for you to understand what this enclosed flux is. First, instead of talking about the enclosed flux, first let's talk about the electric flux. Here you go. First, let us just talk about the electric flux through any surface. The surface can be open, the surface can be opened or closed. The simplest closed surface is that of a sphere. Okay? Think about the electric charge inside an imaginary sphere. You can take the integral through this sphere and find the electric flux if you know the charge here inside. But let's assume that we generate here. We have an electric field in this volume, right? That we know that is generated by this type of configuration. And then we're going to solve a very simple problem. We're going to find out what is the electric flux of this field through an imaginary surface here inside. Okay, I put this surface sideways. It would be something like that if I were to put an angle, okay? A surface that has sides A and B. Let us calculate what would be the electric flux through this surface. The surface, note, see, is not closed. The surface here is an open surface. Okay, so here you go. Let us do a very simple example of how to calculate the electric flux, of a uniform field through a flat surface, through an imaginary flat surface with its plane perpendicular to the field. Okay? So you can have an idea how those integrals are calculated. And before also we go into the closed surface integral. But don't forget, this is a law of physics, okay? You gotta memorize this one. Later on, you're gonna see similar integrals that I'm gonna introduce to you. But let's calculate. Okay, so now what we have here, we have something like the following. Okay, so we go. We are going to go calculate the surface integral over a given area, and in this case it's going to be an open area. So what you have to know, that the vector area of the surface is always represented by a vector that is normal to the surface. Because the surface is a plane surface, this vector area is going to be perpendicular to this surface. Do you see here this perpendicular sign here? You got perpendicular symbol here. It applies not just to the electric field, but also to the area vector. Can you remember that? Every area vector is going to be perpendicular to not going to be perpendicular, it's going to be normal to its surface. For a flat surface, the normal coincides with the perpendicular direction. Go like that. So now we can say for this specific case that the area vector is parallel to the electric field vector. Okay? Let's do a very simple example of calculation of a uniform field through an imaginary flat surface with plane perpendicular to this field. In this case, the area vector of the plane is going to be parallel to the E field. Okay? So when we do this dot product that you see right in here, we can write down that this dot product is going to be the magnitude, the magnitude of E and the magnitude of the A. The magnitude of the A. I still didn't do the integral. It's going to be something like that. Okay, because the electric field is uniform, we're going to have the same value for the electric field anywhere throughout the area of integration. And because of that, I can take out the electric field from outside the integral. Okay? And then for this simple example, we end up with this simple result. The flux across that surface, that imaginary surface, is going to be given by EA. Okay, that's the electric flux. We usually, abbreviate the electric flux with a subscript E, just to emphasize that the flux of the electric field. But why do we do that? Because there is also the magnetic flux. Okay, since I didn't introduce the magnetic flux yet, you can ignore this subscript, but just keep in mind that for whenever we start talking about other fluxes. Simple enough. If our, here you go, remember, for that specific case of a plate, right, of two parallel plates, the electric field can be here written as what? Sigma over, let's see, epsilon. Oh no, he didn't do it. I forgot it. He just gotta put it here. Nope. Epsilon. Yeah. Not. That's what this field is all about. Can we do more than that? Yeah, we can do more than that. Okay. The sigma here is going to be the charge divided by the area, which ends up being the same as this area that you see here. Okay, so here you go. For the specific case of an uniform field, the flux through an area equal to the area of the plate is going to be Q over epsilon naught. Okay. Above, in the above, we assumed that the area of the imaginary Gaussian surface is equal to the area of the plate, the charged plate that is generating the E field, the electric field. Okay, that's one simple example that I'm gonna see out there. Okay, so if we go ahead and imagine a different surface, a different imaginary surface, not an imaginary surface that's parallel to the plates, but imaginary surface that's parallel to the field. Okay, we get what? We get a E dot dA that's going to be equal to 0. So in this specific case here, the electric flux through the surface is going to be 0. Okay. What if we have an angle? Then now we are going to have a cosine of that angle. Cosine of the angle between A and the electric field. Okay? And so on. Here you go. Here's the surface. Here's the surface. What about, here you go. What about the flux, the electric flux due to a point charge? You know, the electric flux of a point charge through a section of a sphere. Okay, what's that gonna be? So think about that here. Suppose that we have a sphere enclosing this charge, right? And this charge is exactly at the center of the sphere. This charge has electric fields that are in the radial direction, which coincide, by the way, with the area vector of the sphere. We can calculate the flux of this case in this case as well. Let's do that. You know, let's now calculate. Here you go. Let's now calculate the electric flux across a section of a spherical surface, Gaussian surface. A section of a spherical surface. Let's put it this way. This is 5:47, right? Let's have a break, right? And then we continue that when we come back from the break. So in this meantime, just think how we're going to do that. And I'm going to see what's going on here. Yeah, this one must be a node one. Okay, lab 38. Let me see if I get a more updated one. Any questions about that? Make sure you practice this type of problems. Let's see if you have this one here. Download. Let me see. I think that I can. If I do this to the cloud, it's gonna take too long. It's easier to download to the computer and then I open it. Okay. 38. Boy, I don't have it. What a shame. Maybe it's here. Yeah, it's here. Okay, good. So my lecture, okay, attendance is here. Good, so let's go. Mario Acevedo, are you there? Nope. Toby? There. Harun, Atif, Musa? Genesis Bell? No. Now Jennifer Camarillo? Robert Faust? Pedro Flores? There. Lawrence Flores? Alexander Garcia? Sung Ham? There. Brian Inês? Athena? No. Dylan Martinez? Rafael Mercado? Alexis Nigret? Abraham Perez? Nope. Nicolas Pisano? Nope. Ramon Quintana? There. Ali Sharabi? Okay. Kenny Villagomez? Patrick Villavazov? Nope. Nolan Williams? Nope. Nope. Let's see how many fields we have here. 14. Dois, três, quatro, cinco, seis. 1, 2, 3. Is 5:50 right now. Break until 6:05. Okay. Break. Till 6. Let's do 6:06 p.m. Here you go. I'm going to stop my recording here. Remind me we are back here. We're going to do another example for the flux of the electric field, but now in this case we are going to do the flux of the electric field. For a point charge, the field of a point charge going through the section of a spherical surface that's located only on the first quadrant. The illustration would be something like that. Don't forget this thing is it's supposed to be a three-dimensional drawing, right? We have how many quadrants do you have? Do we have, right? How many quadrants do you have? Is that the three-dimensional space? Think about that. Let's do this drawing. Let's do a drawing, a three-dimensional drawing, so you can count the quadrants that we have here. So here you go. I'm gonna get this. I'm gonna do here. Format shape size. Maybe format shape. Let's see here. Yep. Like that. I'm gonna do a black so you can see it better, and I'm going to increase. Okay, that's my first axis. Let's say this is I'm gonna do that. I'm gonna take out the electric fields because I want just to count the quadrants, right? Like that. What I want to do, I want to make this guy here to the right, not to the left. And the next axis is going to be this one here. We're gonna draw in such a way so we give this illusion of a three-dimensional drawing, right? When we draw those things, we usually represent this axis right in here as being the x-axis. This one is the x. This other one here is the y. And then we're going to draw the z-axis. How many quadrants do we have here? Let's count them. Okay, we have this one here, 1, positive y, negative x, positive z, 2, 3, 4. Okay. One, two, right? It's not 4, it has to be more than 4. Let's see. 1. Well, let's go here in my notes. not this one here. Okay, calculate the flux surface. Okay, it's 8. Okay, it's supposed to be 8. Uh, it's 4 for a xy, right? But in the three-dimensional space, it's gonna be 8. Okay, so what we are doing, we are getting, you know, a surface only in this region right in here. A spherical surface only in this region. So so what you gotta know? You gotta know that the electric field is radial, the charge is centered, okay? The electric field is radial, and in this specific case, the area vector has the same direction as the electric field as well. So here you go. Uh, break into calculate the electric field across a section of a spherical surface located in just uh, one. Is it a quadrant here? Let's see. Oh boy, I don't have. Uh, let's keep track here. Let's see. We have, here you go, positive x, right? Positive x, positive y, and positive z. And then we have negative. They're negative, right? Negative x, y, and z. Let's make sure it's 8, really. Negative x, negative y, and negative z. Just figuring out a better way to explain that to you, right? So we can have combinations of those, right? First, what we have in, oops, in this one here, let's see, 1, 2, and 3, this volume that you see here is the positive x, y, and z. Positive x, y, and z, that's one possible volume. Okay, one. Sometimes it's good to do that. Here you go. Then we have positive x. Yeah, we did positive x, positive y, positive z. Then we have positive x, positive z, and negative y. Positive x, positive z, and negative y. Negative y, right? So here you go. We're going at the top first, right? Then we have, yeah, it's 1, 2, 3, 4 on the top and 1, 2, 3, 4 on the bottom. There are 8, right? Exactly 8. Make sense? Sometimes we have to stop and think about it, right? Positive x, positive y, positive z, and negative y. The next one is going to be what? Negative x, negative y, and positive z, right? Negative x, negative y, and positive z. And then next one, we're gonna have, let's see here, we did this front, we did this one, we did this one. Now we're gonna do negative x, positive y, and positive z. Negative x, positive y, and positive z. Positive. Okay, so we have a positive, 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 negative, positive, negative, negative, positive. Okay, good. So we have 8. And then we repeat that for negative z. Okay? Another way to do that is just to look at the x and y axis and then add the positive z and the positive and the negative z, right? Quadrants in the x and y axis in the two-dimensional space, right? It's not, shouldn't be quadrants in the x, y, z space. Should be called another name. Another name that's not quadrant, right? So it's a total of 8. Okay? So here we go. So yeah, I don't know how they call that. It's quadrant in the two-dimensional space. In the three-dimensional space, I do not know what they call it. Have you ever heard octaves? Maybe octaves? Huh? I can't hear you. How do you spell it? Louder, please. Louder, please. Octants. Octants. Okay. Yeah, there's quadrants and octants. Good. Octants. And then if it is a four-dimensional space, you have, well, you gotta figure that out, right? You have to figure that out. It would have be negative t and positive t, right? Octants. Let's take a look at the internet here. Octants. Octant. Let's see. Yeah, oh no, that's not the octant. Octant is an instrument, solid geometry. So it's one of the 8 divisions of the Euclidean three-dimensional coordinate system. Cool. Octants. Okay, so I'm gonna fix that in my notes, right? Here you go. It's not quadrant. Calculate the flux spherical surface of the first octant centered at the point charge. And then I'm gonna save this guy as a version 55. Okay, so let's calculate that. Yeah, so we got it. It's an octant. Let's write down the integral. Okay, here we go. Or a point charge in the origin of the x, y, z coordinate system. Find the electric flux, and for a positive point charge, find the electric flux through the first octant. Here you go. Solution. Here you go. I'm gonna get this one because we have flux through uh through the section of a spherical surface in the first octant only. It's not a closed surface, it's an open surface. So here you go, flux. Flux is going to be something like that. Okay, here you go, E dot dA. Because the charge is centered, the area vector of the surface is going to be parallel to the electric field of the charge. Okay, I'm gonna even be better. I'm not gonna put the magnitude of E. I'm gonna just put E. No, I have to put magnitude of E. Leave this way. Yeah, and magnitude of dA. Oh, don't forget, should be the cosine, right? Yeah, there is one more thing here. It's better if you put the cosine here, so we know whether the flux is positive or negative, right? In this case, the angle between the E and A is gonna be 0 degrees. Okay, because if it was a negative charge, this angle would end up being 180 degrees. Okay, so we have to put the cosine angle here to account for the sine. Okay, now what can we do? The electric field through that spherical surface. Remember, the electric field is not uniform. The electric field decreases as you move away from the charge, right? Is stronger here, weaker here, weaker here, weaker here. But the magnitude of the electric field on a surface that's centered at the origin where the electric charge is the electric field on that surface is going to be, the magnitude of that electric field is going to be the same, right? Make sense? So because of that, we can take out this E from inside the integral. And we are left with this other integral here. Here, the area is going to be the area of the sphere, which is 4 pi r square. I have to, to state for a positive point charge, find the electric flux through the section of a spherical surface of radius, I didn't put that information, r, located in the first octant. Okay, so I'm gonna write that down here. The area of a surface is 4 pi r square, but because we are talking about the first octant, we have to divide it by 8. Okay. For this specific case, we already know that the electric field of a point charge is going to be at that spot, is going to be what? The electric field of a point charge at that specific spot. You put the charge Q for a positive charge Q. You gotta put a positive charge Q as well in the origin. Okay. KQ KQ over R square. Like that. That's what the electric field is all about. The R square cancel out with the R square. The 8 cancel out with the 4. Can we do better than that? Yep, we go. KQ pi divided by 2. Maybe we can do better by changing this guy to 2 pi. 1. You got 2 pi is 4 pi, right? Let's see here. K can be here written as 1 over 4 pi epsilon naught. Yep. That's the relationship between K and epsilon naught. Okay, so here we go. And then we gotta multiply for everything else, right? Okay, the pi cancels. Oh, the K disappear. Can leave it either in terms of K or in terms of epsilon naught. The pi disappear. We end up with 8 downstairs. Like that. Q over x8 epsilon naught. That's what the flux is through that surface. That's a very good exercise to understand what's going to come next. Surface area. And here you go. Oops. Now, the next question is, what about the electric flux through this spherical surface that's not centered at the origin? Okay? Ask yourself about that. This problem is very difficult to calculate. It's not easy. You gotta do some numerical integration, some serious numerical integration, because in this case, the electric field is not necessarily parallel to the area vector. Okay, the area vector here, this sphere is centered, the center of the sphere is a little bit offset, so the area vector doesn't point in the same direction as the electric field vector. So this problem here you cannot calculate easily. It's very difficult. You have to use numerical integration. Okay. Now here go. Remember the electric field lines of a point charge, right? And now we are going to use the Gauss's law. Okay, think about that, right? Here you go. X and Y, center of the charge, electric fields are in the radial direction. We have a spherical surface that has an area vector that's, you know, parallel to the electric field. We just did that, right? Those area vectors are normal to the surface. Okay. And so what we're going to do here? Okay, now we are going to use Gauss's law to derive Coulomb's equation, Coulomb's law. Okay, it's possible to use Gauss's law to derive that law. Derive Coulomb's law from Gauss's law. It's possible to do that. Suppose you don't know Coulomb's law, but you only know Gauss's law. Can you derive Coulomb's law? Yeah, it's possible. So how do we do that? Your starting point now will be Gauss's law. We're going to start talking about closed surfaces, okay? Here you go. Let me get here, writing here. Here you go. Here's the closed surface. Right in here. That's Gauss's law. You have to draw that surface, that spherical surface around the charge, and you go ahead, you say that the spherical surface has a radius r, lowercase r. Okay? Point charges has electric fields that are radial, will always be radial. Okay? Point charges. Things become more complicated if you have other charges nearby. Okay, the area vector is also radial. Both the electric field and the area vectors, both the E field and area vectors are radial. Let's see, the E field is radial because we have a point charge. The area vector is also radial. The area vector is also in the radial direction. The field is radial and away because we have a point charge. Since the charge is positive, the field points away from the charge. Okay. The area vector is also in the radial direction and points away from the charge because the area is always away from the convex surface. That's how we choose the direction of the area vector, okay? The direction of the area vector will always be pointing away from the convex surface, never towards, never away from the concave surface. Okay? Can you remember that? So now we can rewrite our integral as being just like we did before. Here you go. Like that. this one here. Uh, cosine of 0 again. I'm just doing the regular dot product here. Okay. And I have chosen a surface of radius lowercase r. Okay. So here go, the next step, cosine of 0 is 1. And by the way, the charge enclosed by the surface will have a value Q, capital Q, just like I mentioned previously. Here you go. Derive Coulomb's law from Gauss's law for a point charge big Q greater than 0. Big Q greater than 0. Okay? That's where the Q enclosed comes from. Okay? The Q enclosed is the charge enclosed by the Gaussian surface, by this closed imaginary Gaussian surface. What's next? Okay, the cosine of 0 becomes 1. Oops, becomes 1. The electric field over the surface is said to be the same because it's at the same distance from the charge. Okay, we are not using Coulomb's law here, remember? Remember, because the distance from here to this point is the same as the distance from here to this point, it's reasonable to state that the magnitude of the electric field over the surface is going to be the same as well. Okay, 1 times 633. So we can take it outside of the integral. The area of the surface enclosed the charge, we know that's going to be 4 pi lowercase r squared. And now with this equation, we can finally determine Coulomb's law from Gauss's law. Gauss's law is a far more genetic statement. It's going to be what? Q divided by 4 pi epsilon naught r squared. Like that. So, what you have right in here, don't forget 4 pi epsilon naught is k, right? 1 divided 4 pi epsilon naught is k. Like that. KQ r squared. That's one example. We have 10 more minutes to go. Let's look at another example. Let's see what's another example we can have here. Oh yeah, we can come up with a solid sphere. Okay? Uniform charge distribution. Oh, uniform charge distribution. So here you go. Uniform charge distribution. It's spherical distribution of charges. Uniform. Remember, we didn't calculate the electric field of a uniform charge distribution using the regular procedure. Now we're going to do that using Gauss's law. It's going to be in a much easier fashion. Gauss's law is nice because it can calculate easily the electric field of certain charge configurations that have symmetry. Okay, it cannot be applied to every charge configuration, but some charge configuration, yeah, we can do that, provided the charge distribution is symmetric. Okay, so here you go. It's a spherical distribution, solid spherical distribution. You have charges from uniformly distributed from the radius equal to 0 to radius equal to r. Okay, here you go, radius big R. Let's put the x and y axis. Just like before, okay, because the charge is uniformly distributed in this volume, it's very reasonable to assume that the electric field is going to have a radial direction. Okay? You don't have more concentration of charges here than there. No. Everything is uniformly distribution. So that's a very good assumption here. And then what else? We are going to calculate first the electric field at a distance lowercase r greater than big R. That's what you're going to do. Okay? Net charge of this sphere is big Q. Okay, so let's go. Right here. Uniform charge distribution is uniform spherical charge distribution of radius r and net charge dq. Find its electric field for r greater than r and r less than r. We're going to do that for both. Start with r greater than r. Okay? Because we have a spherical symmetry, it is reasonable to state that the field will be in the radial direction. Okay. Okay. Draw a imaginary sphere at a distance r greater than big R. No area vector. But let's put big Q greater than 0. Okay. Area vector parallel to the electric field. We have already seen a problem like that before, right? It is exactly the problem of the point charge. Here you go. I'm going to just copy and paste here. What's not exactly equal to the problem of the point charge is for r less than big R. Okay, electric field parallel to the area vector. The angle between them is 0 degrees. The electric field intensity is the same along on this surface, on this imaginary surface. Consequently, we can take the magnitude of the field outside the integral, and we are left with the integral of the area of the imaginary sphere, that's 4 pi r squared. So what we have here, and not only that, the enclosed charge is going to be big Q as well, because this sphere encloses the whole sphere. This imaginary sphere encloses this whole charged sphere. This whole charged sphere has a net charge of big Q. Okay? So this thing is just like the point charge problem. What's not like the point charge problem is for r less than big R. But let me finish this one first. Here you go. Okay, right in here. Yeah. This one is just like this one is just like the point charge. However, for r less than big R, the problem is different. Why is that? Well, the problem is different because now we are not going to have a net charge Q enclosing the sphere. Okay? Enclosure. Okay, now we have the sphere, radius big R, the whole sphere has a charge big Q. But then we want to find out the electric field within this void, in this volume within inside the sphere. Small r less than big R. Okay? So how do we do that? Okay, so we have to account for the enclosed charge in this surface. That's what we have to do. The charge enclosed by this surface is going to be less than big Q. Make sense? So let's go step by step here. Different sphere, smaller sphere, right? Gaussian surface. is a sphere smaller than the spherical distribution. Okay. But the electric field is still the same. And by the way, what I have to do here, I have to, let's start with this one. Let's start with this one instead of the other one. Let's start solving the right side of the equation, right in here. Okay? So what we have here on big Q? What having big Q here is going to be less than big Q enclosed. It's going to be less than Q, right? So how do we calculate that? Oh, it's simple. What we do here, we get the volumetric charge distribution and multiply by the volume that the volume enclosed by the spherical surface. We go epsilon, okay, like that. Okay, this volume is going to be equal to what? Okay, just this rho is going to be what? It's going to be big Q divided by the whole volume of the sphere, 4/3 pi r cubed. Make sense? That's what the charge density is all about. The volumetric charge density is all about. Now, this volume that you see here is going to be less than this other volume. Okay? Instead of big R, is going to be lowercase r. What time is that? 6:44. You still have time. Okay? And then what's going to happen? Let's continue here. There are some simplifications that we can make. 4/3 of pi can be canceled out. R cube is going to go downstairs. Like that. That's what the right side looks like. That's what the right side of the equation looks like. Remember when we did for the surface outside the sphere? We didn't have QR cube over R cube. We had only Q, right? So what we have right in here is replaces what you have right in here. Okay. E for pi r squared. And now we can finish our electric field for a uniform volumetric distribution of electric charge. Something like that, right? The r squared cancels out with the r cube. R squared cancels out with the r cube. We have a linear variation of r. The 4 pi goes downstairs, becomes 4 pi epsilon naught, which by the way is k, right? I'm going to rewrite that in a simpler way. KQ R lowercase r over r cube, like that. Okay, so that's what happens to the electric field. The electric field inside the sphere increases linearly. Inside the sphere increases linearly. You go outside the sphere, it decreases linearly. Okay, is this electric field continuous at the surface of the sphere? Let's see. You know, the value of this field at the surface of the sphere is what? At the surface of the sphere is going to be, something like that. KQR squared. What about the value of the electric field for that other expression at the surface? At the surface is going to be what? Same thing, right? So the electric field is continuous at the surface, but not its derivative. Not its derivative. Let me see if I have a plot here of this case. No, I don't have a plot. But if I were to plot the electric field, the intensity of the electric field against the distance r, I'm going to do like that. Here you go. Against the distance r. Let's see if I can get it good. Let's get it right. Whoa. Oh, 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 oh. What we have? We have that the electric field increases linearly. We go. Oops. Can I get that? Huh. It's something like that. Okay. It increases linearly and then decreases the square of the distance. The electric field is continuous, yes, but not its derivative. It's something like that. 6:49. We can stop here and I'll meet you again on Tuesday.